Welcome. Hello. My name is Jorge Vasquez. I'm a principal engineer with Amazon Cloudfront. Next to me is my friend and colleague, Shailu Mishra. He's a software development manager also with Amazon Cloudfront. This is maintaining security and availability on the unpredictable internet. This mouthful title is not the title I wanted. The title I wanted was Failure is an Option. And that's what we're going to be talking about. And that's the title you guys will remember. So let's get started. Our agenda for today includes a brief introduction to Cloudfront. Next, I'll be talking about our tenets, the things that are important to us and that guide and inform our design, our operations, and our procedures. And finally, I'm going to talk about all the things that threaten availability in Cloudfront. We're going to go over a few case studies, and we're going to go over a few design patterns of things you can also use in your own softwares, in your own services, to keep them always available, just like Cloudfront is. First, let's take a look at Cloudfront footprint. This year, we have 199 edge locations, points of presence. I call those POPs. That's the one acronym I cannot escape from, so I'm going to be saying POP a lot. It means point of presence. It's a small data center, usually in some kind of urban scenario, where we deploy our hardware, our software, and we peer with network providers, people like Comcast, Verizon, AT&T, and other providers around the world. We are in 199 of those. Last year, when I was talking here at reInvent, we had 150. So that's how fast we're growing. We built almost one per week this year, on top of the ones we had to refresh. We are in 78 cities and 37 countries. That's 8 countries more than last year. It's very important for a CDN to be everywhere. That's how we make sure your customers, the people who use your applications, can use them as fast as possible from anywhere they are. So I'm going to start this presentation by talking about tenets, the things that matter most to us. It's very important to know what they are, because those priorities inform everything we do in Cloudfront. They tell us how to design the system, how to create our processes, how to do operations. The first one is obviously security. Security is about trust. If you are not secure, if you expose data, if you don't treat your data carefully, we lose your trust, and more importantly, you lose your trust with your own customers, with the people who use your own applications. So nothing is more important to us than security. Even availability, which is the main topic of this talk, everyone in Cloudfront, every single engineer who operates Cloudfront is ready to make a judgment call and sacrifice availability if necessary to maintain security. Next is obviously availability. A CDN is about having your application delivered everywhere, your content delivered everywhere. We are willing to make sure this happens no matter what the cost. Performance, which is our third priority, comes second to availability. This means that if something goes wrong, something unpredictable happens, we are willing to deliver a slower experience temporarily to make sure your content is always available. So failure is an option. So there is a paradox in a system like Cloudfront, which is a massive system, highly available, and very complex. It's impossible to make such a system out of super highly reliable components. We have to use things that are intrinsically unreliable. Examples here are the ones on the screen: SSDs, power supplies, network links, and many more. So how do we do that? Well, as engineers, one option is we build a robot. So meet Cloudfront. This is Cloudfront. And it's fair for customers to see Cloudfront as a robot, because Cloudfront is an API-driven service. You don't have to do anything if there's a link down somewhere on the internet. It's all on us. And when I mean on us, it's all automatic for you. So yes, Cloudfront can be seen as this autonomous, totally self-healing system that behaves like a robot. But as many of you know, you're also developers yourselves, you know that we can never automate everything, that there is always the engineer steering things around. So let's try a different model for Cloudfront. The guy on the left is Cloudfront, the guy on the right is me. I'm looking good today, aren't I? So in this model, Cloudfront is a lifeless puppet that engineers like me are steering and make sure it works all the time. That's not fair to Cloudfront. Cloudfront is not lifeless. Cloudfront is not fully steered by engineers. There's a lot of automation that goes on, a lot of things that we make it react to on its own so that availability is restored in much shorter time than engineers would be able to. Also, there are things that happen beforehand, like allocating traffic to the right locations to avoid like links down or locations that are out of capacity. This all happens automatically without any involvement of engineers. So this is not a fair model to Cloudfront. So the reason I took this detour into this robot and the puppet was to introduce another element to our availability analysis, the human element. So Cloudfront is this collection of hardware, software, and people. And these three components is what we use to make sure Cloudfront is always available. So if you were in my shoes and had to design components of Cloudfront, which one of those on the screen would be the ones that are most at risk of causing availability threats to Cloudfront? Before we go there and answer this question, let me introduce a concept that is very useful to understand the threats, the concept of blast radius. Failure is an option, as I said before. So if something fails, it's important to know in advance to which extent the system will be impacted. That concept is super powerful in allowing us to design the system in a way that will contain failures to an extent that will not impact the overall customer experience. So let's look at the components I mentioned before and see what's the blast radius of a failure in one of them. An SSD, a solid-state drive. If one fails, it impacts one server. I think it's fine. I have tens of thousands of those running in the 199 data centers I mentioned before, so I can live without one of them. Not a huge blast radius. I'm good. Power supplies, exact same story. Network links, there's a different story. It depends on the link. For most links, we have redundancy. So for 5 seconds or so, BGP, the border gateway protocol, will do its thing and reconverge and find a different path, and things will be good. If many links isolate a POP, then you can have a single ISP, a single network provider being isolated from that one POP, and then you have to route this traffic somewhere else, or it can even lose a full POP, like a full city can not have CloudFront anymore. This is also not a huge problem. I can serve traffic to Las Vegas from a city which is not Las Vegas. Might not be as fast as it would be serving directly from here, but it's going to still work fine. Now comes people like me. If I make a bug, not that I ever do one, but if I was to write a bug, it would impact all of CloudFront because my software would eventually be deployed to all of CloudFront. If an engineer gets paged in the middle of the night and has to make a configuration change, same story. All of CloudFront gets impacted. So with that in mind, I'd like you guys to meet the biggest threat to CloudFront. Anyone seen this guy? Okay, so how do we reduce the blast radius of code changes? I'm not going to lecture you on good engineering discipline. You're probably very well aware of that. You know how to do code reviews, tests, continuous integration and deployment, wave deployments. I'm going to just say that you can also do the same things we do in your own services using services like AWS Code Pipeline and the AWS Code Deploy. So let's take that idea of reducing the blast radius of code changes and apply that to a real use case inside CloudFront. So in CloudFront, we have this system we call the change propagation system. In order for points of presence to answer requests, HTTP and DNS requests that your users send to them, we need them to have a copy of all the relevant configuration. We don't want these points of presence to have to go back to a central location, call a service or a database or something to fetch the configuration. First, that would take too long. Second, that would introduce dependency on the central system for every single remote location. So we want our edge locations, our POPs, to be what we call statically stable, which means if they get disconnected from other systems around the world, they are still there and they are still working and serving your content. Perhaps with another configuration, but still serving your content. So this is how it works in CloudFront in a rough perspective. Users, either us to make internal changes or you making API calls, call the API service, which stores data on the database, and eventually these changes get picked up by the systems we call the parcel builders. Parcel builders fetch configuration changes from the data store, put them into S3 buckets, multiple S3 buckets in multiple regions, and edge locations, points of presence. They go there and they fetch these configurations to use. This is how the system works in a nutshell. You can see I added 3 parcel builders there because I have a wave deployment. So let's see what happens if a random engineer writes a bug. So bugs go to the first wave of deployments for the parcel builders. And then something interesting happens. This first server deploys buggy configuration to all the S3 buckets, and that finds its way to all the CloudFront POPs. We don't want that. The reason I'd like to show it to you is because just doing wave deployments when you have distributed systems with components talking to one another is not enough to contain the blast radius of code changes. So what we do is introduce a concept which we call in CloudFront striping. A stripe is a collection of components in different parts of your system that are isolated from one another when it comes to ingesting configuration, for example. So in CloudFront, in this case, we have multiple S3 buckets, not just a single one, but I just draw one per stripe because it would be easier. But in this case, the bug goes to the first wave, which goes to only this set of S3 buckets and only goes to one point of presence. This is good because now, if I get paged to resolve this issue, I can take a very quick mitigation path, which is removing from service the affected POP. I told you we have 199 of them, so that's roughly 0.5% of my fleet. I can safely do that without impacting the usage of the service, without impacting the customer experience. So this is something you can also do when building your own services. Make sure that distributed components don't leak a change which was supposed to be contained to a very small deployment everywhere when they talk to one another. Next, let's study a real failure that happened in CloudFront. We call that the case of the poisoned latency measurements. CloudFront has to measure latency from every single network around the world to every single point of presence. We do that to find out, as close to real time as possible, what is the fastest path from every user to every POP, and then select the best POP to serve the content. Networks get congested, they change all the time, so we have to do that in real time. This data is aggregated in a central location, regional deployments, and then we ship this aggregation back to the DNS servers that also run in the POPs so that they can make a decision and route people to the best POP. The change we wanted to make was to introduce the concept of city. So I told you before, we had 199 POPs in 78 cities, which means some cities have more than one point of presence. The change was to aggregate all the measurements for all the POPs in the same city into one data point. The reason for that is to have better statistical properties. If I have more data points, I have tighter confidence intervals, I have better data to work with. So that was the change. We'll pick this table that has POPs in one column, network in columns, and networks in rows, and introduce cities in columns as well. That was the change. By the way, this diagram you see on the screen the TCP three-way handshake. Yep, it turns out college was useful for something. We use it to measure the round trip time. We measure the time it takes from every single connection in Cloudfront between the SYN ACK packet and the ACK packet. And we call that the round trip time. So let me go step by step and tell you what happened during this change. First, we deployed the change. That was expected. That's what we wanted to do. Second, we had an alarm, velocity check failure. What is this velocity checker? That's a pattern that you can also use in your own systems. Anytime you have data flowing from one component to another, in CloudFront, we compare the configuration in this case, but it could be other types of data. We compare the configuration to the previous version of the configuration. If it has changed by too much, in this case it's a simple file size comparison. So if it has grown too much or shrunk too much, we say something is wrong, something is fishy, I'm not going to allow this configuration to go through. In this case, this was expected because we introduced 78 entries in a file that had 199 entries. So the file grew by more than 1/3. That tripped off the alarm. So the operator, the person doing the deployments, overrode this velocity check. This was a planned step in our change. That brings me to something else I'd like to talk about today. Whenever we have to do changes in a production system like CloudFront, we always write down these changes before we do. We write a change plan that includes all the steps you have to follow, that has precise okay. That includes precise rollback steps. That includes which metrics and logs and alarms you have to look for when determining whether to roll back or not. I have to admit, when I first joined CloudFront, that felt like a lot of red tape. Every change I have to do, I have to go and write this document. But as time passed, I grew to love this thing because it allows us to think in advance about everything that can happen and not have to make split-second decisions when something is going wrong and our customers are being impacted. Just like you don't want airplane pilots to get creative, you also don't want on-call engineers to get creative. You want to have procedure. You want to have this procedure reviewed. So, and that is super important. So in this case, that change document said, this alarm will fire, you are okay to override it. So far, so good. So new files get generated, including the cities. They get shipped to all the DNS servers, and then something unexpected happened. We had another set of alarms firing, telling us that every single change propagation to our DNS servers were not being propagated. They're not going in sync. So what was going on? To understand that, let's look at how the DNS servers ingest changes. So this is our DNS service. And these are the end users making calls to the DNS service to get IP addresses to which to connect to. This is so important to availability, I'm going to add a crown and call it the King DNS server. Always has to be up and running, otherwise CloudFront is unavailable. This thing can never die. So one model would be to get the configuration files from S3 and pump them directly into the DNS service. That model is dangerous though, because if somehow bad changes get into S3, boom, the king is dead. You don't want that. So instead of doing that, we take a detour. The detour we take is sending the data to a system we call the food waiter. The food waiter sends the data to a copy of the DNS service. It's the exact same code, run with slightly different configurations to not be exposed to the outside, so different set of ports and IP address bindings. And then food waiter gets this configuration to the food taster and sends 5,000 DNS queries to it. If the answers to these queries are sane, and if food taster doesn't die, only if those two situations are met, we give the configuration files to King Tiny. So what was happening in this case is that food taster was choking. It was ingesting poisoned configuration and was dying. So it was doing its job, which is good, but it also meant that no new configuration could flow into the DNS service. That's an interesting design pattern. It doesn't apply to everything, but in places where you can do that, it saves you by transforming what would be a service outage, in the case of Cloudfront, DNS being non-functional would be a service outage, into an inability to ingest configurations. Here, I'd like to talk about how we think about Cloudfront services. We separate them all into data plane and control plane. Data plane are DNS and HTTP components, the ones that have to be available for your customers to perceive your application as available. Everything else, the systems that we use to steer Cloudfront, the systems that you guys use to configure Cloudfront, we call all that control plane. If push comes to shove and I have to choose between the data plane and the control plane is taking the hit. And that's exactly what this food tasting design does. It transforms what would be a data plane impact into a control plane impact, which is totally according to my priorities and a great deal. A deal I'm happy to take any day. So just a recap, what went wrong? First, someone wrote a bug. In this case, the bug was that we took this list of pops from this table with latencies, and we thought this was a list of pops and tried to look up pops in other configurations. And now this list of latencies also had cities, and cities are not pops, so there was a mismatch there, and boom, the thing crashed. Bad, bug, things happen. Food taster were choking, no configuration could be ingested, that's bad. What went well? Well, it did its job. It died in place of the king. That's the whole job of food taster, so great. And no data plane impact. Next, I want to talk about bad weather. Internet weather, things that are outside our control. Good thing for you, Cloudfront team is based in Seattle, and we know a thing or two about bad weather. It gets worse. So the gentleman who wrote this comic is Matthew Inman. He's also from Seattle. You might know him from the Oatmeal. He was kind enough to allow me to use his comics and tell you that as customers of Cloudfront, you have a big advantage of having people used to bad weather. Jokes aside, let's take a look at what constitutes bad weather. One of them is links congested. So one type of link that can get congested is Amazon-controlled links. Links that are connected to a router that we own. We have telemetry on those. We know which traffic is going on those. We know the network topology before these links, so we know what should go there. So the first thing we can do to avoid this kind of bad weather is to have what we call active network capacity management. So I should not send to this pop on this picture more traffic than it can take, than this link can take. Even if other links are fine, if the pop has enough CPU capacity and I/O capacity and everything else is fine, we don't send to this point of presence more traffic than the links downstream of it can take. Next, since we share these links with other services, and since sometimes there are flash crowds, people send more requests because something exceptional happened, we also have automatic traffic engineering. These are network systems that work on these routers and are able to steer the traffic towards different links if necessary. For example, sometimes we have links that we call peering links. These are links between Amazon and network providers, direct links to someone like AT&T. If this link gets congested, we can spill over a little bit of traffic to a link from a transit company, which is a company that charges us more, but is able to send traffic to anywhere on the internet, not just to that one network we are peered with. We have systems that do that automatically. One interesting thing for both of these systems, active network capacity management and traffic engineering, is that current traffic is different from demand. So if we look at a link which is congested, let's say 100 gigabits per second link, 100 gigs link is congested. If I'm able to move half the traffic to another link, one would expect that the remainder amount of traffic traffic would be 50 gigs. In practice, that's not the case. Usually what's going to happen is that this 50 gigs are going to expand and possibly fill up the whole remainder 50 gigs. Why is that? That's because protocols like TCP, they expand in bandwidth to fill up the smallest link in the path between the two endpoints. Another one that causes the same kind of behavior is adaptive bit rate, ABR, in videos. So you're watching this video, 720p, the link is congested, that's all you can get. Automatic traffic engineering kicks in, got more bandwidth, boom, your video player switched to Full HD or to 4K automatically. So traffic that we measure when links are congested are not demand. And that makes things way more complicated for us. And that sometimes makes that those systems, they have to be iterative. They have to run and run and run until congestion is dissipated. Finally, as a last resource, we have to engage the engineers. So again, in this case, Cloudfront is both the robot and the puppet, right? We have these automatic systems, but worst case scenario, we engage engineers to manually steer the traffic. What if the link that gets congested is not directly under Amazon control? First, I don't even know where this link is because I don't really have a map of the internet. Whatever map I have would be a layer 3 map, which is not reflective of reality. There's no way I can install telemetry in someone else's router. Amazon is big, but not that big. We cannot do that to other people, right? So what can we do to avoid congestion in links we do not control? What we can do, as I told you before, is measure latency and measure that all the time, almost in real time. Why it works? Because this is a rough model of a router. A router in this rough model is a crossbar that connects input interfaces to output interfaces. Before every output interfaces, there is a buffer. This buffer is there to accommodate spikes in traffic and then not drop these packets. The thing is, when you are routing more traffic to an interface that it can take, eventually this buffer fills up completely and starts discarding packets. These buffers range in size, depending on the router, from a few microseconds to tens of milliseconds. The big ones, the ones that are used to interconnect network providers like Amazon and big ISPs, they usually have these big tens of milliseconds ones. So when this link is congested, the pop on the top will see higher latency to those users than the top pop on the bottom. Cloudfront will realize that automatically and reroute the traffic to be served from the pop on the bottom, thereby avoiding the congested path. That is automatic. I don't even get paid for that, and we are able to find the best path all the time. Next kind of problem are links down. Obviously, we never buy links like the ones you're seeing, but sometimes you buy something and you get something else. This is a real picture of a link that used to carry Cloudfront traffic that someone on the ground took for us. This is in a developing country, and you might think, yeah, that only happens in poor places. Not really. So in New York, of all places, I was doing some research, and I found that in 2015, they had 3,700 manhole fires. That's 10 manhole fires per day. Wait, it gets better. In 2016, they improved a lot. They only had 1,900 manhole fires. So they are improving, but these things are still very, very common. So links go down. In rich countries, poor countries, everywhere, links will go down. So what happens when a single link goes down? This is a common scenario. It happens because of these things we just saw. It happens because people excavate. It happens for many reasons. Most of our links, if not all of them, are redundant. We buy links that follow different physical paths. When you connect to network providers, we connect using multiple routers to multiple routers on their sides in a mesh setup. We do all we can so that BGP fails over in 2 3, 4, 5 seconds at most and finds a path which is available. This, at the worst case scenario, will transform what would be an availability issue into a performance issue. Remember my tenets? That's good. I'm making a good trade-off here. I'm trading availability for performance. Great. And that's exactly what happens in this case. If necessary, someone will get paged and go there and fix the broken links, or firefighters will put down the manhole fire. What if multiple links are congested? This is a very, very rare event. We saw some of those, for example, when there were hurricanes in the Caribbean, then you have a big transit place getting flooded. These things can happen, but they are very, very rare. What we do in this case is have our DNS servers health check all the points of presence before handing out IP addresses to them. So they will never hand out one IP address of a POP they cannot health check. That's our last line of defense. And you can do the same thing, because you can program the same types of health check on Route 53 and make sure you never hand out IP addresses of a server or service or load balancer, whatever that is. In my case, it's a POP that is down or not really working. That takes, in our case, 45 seconds. And after the fact, an engineer will go and make configuration changes to Cloudfront to make sure that the system reconverges and traffic is balanced correctly across different locations. So this is a diagram depicting what happens. As you can see, the POP number 1 is closer to the users, but you're handing out IP addresses of POP number 2 because the DNS server cannot health check POP number 1. So this is a graph that shows one of those examples. This is a real-life example happened in October 26 in the Dallas area in Texas. The green line there is the number of HTTP requests processed by that POP. And the blue line is availability as measured by our customers, by browsers running JavaScript test probes. As you can see, as soon as the event happened, we have this very small drop. We dropped to 95% instead of 99 something availability. That lasted a minute, and availability was restored. What happened there, you can see on this second graph. The green line is still the same thing, and the blue line here is the number of DNS responses carrying IP addresses from the POP that died. So as you can see, 1 minute later, these 2 vertical lines there, we stopped handing out IP addresses from the POP that could not be health checked, and that restored availability immediately. So that's something you can also do, just use Route 53 health checks. Next, I want to talk about environmental issues. Don't worry, no climate change talk today. I'm going to talk about these very rare situations that we treat just like multi-link failures. In one example, a long time ago, when we still used a lot of these rotary hard drives, spinny drives, we had a fire suppression failure in one of our data centers. The fire suppression equipment released a lot of CO2, pressure increased, the hard drives heads crash landed on the platters, and they ruined the hard drives. We have power outages, super rare these days, but sometimes they happen. Cooling equipment failure. I don't really care what those things are. Important thing is they will fail health checks. I will route away from this, and eventually someone is going to go there and get it fixed. That's how it should be treated. So it's just like a multi-link down. There's a big failure that isolates some hardware components. I route away from it. Another type of bad weather is our components that fail regularly. I use the acronym MTBF, mean time between failures. So every component like SSDs, they have a mean time that the manufacturer says is how often one of those will fail. I told you we have tens of thousands of servers, which means we have hundreds of thousands of SSDs. Statistics don't play in my favor here. They will be failing all the time. So what can we do for failed SSDs? We can automatically sideline them. I can take them out of rotation if they happen to fail. I just have to build a system in my POP that detects this failure and then puts it away. One problem, though, with such a robot, that is a robot, a system that detects this failure, is that there is the potential for what we call the suicidal pact. What is a suicidal pact? Imagine there is a specific workload that never came before. A new customer joins CloudFront and sends some kind of specific workload that somehow confuses the system that detects hard drives are down. In this example, one thing we use to detect that hard drives are not working properly is the I/O latencies, is how long they take to respond to one I/O request. When these numbers start to go up, we say, yeah, this hard drive is probably bad. But I can very well imagine some specific workload being thrown at these hard drives that will make them increase latencies, even though they're completely fine. And if that was to happen, all of the drives could be sidelined worldwide at the same time by this malfunctioning robot. We don't want that. We want to sandbox robots so they don't go crazy and damage our whole system. So for every automation you have that has the potential to commit a suicidal pact, you need to build some kind of guardrails. In our case, this is what we did. The CloudFront POP detects a bad hard drive. It sends a message to this system that we built that will contain a simple question. Can I remove this one disk from rotation? If the answer is yes, it goes ahead and removes the disk from rotation. If the answer is no, because this central system has a global view of everything that is happening, so it knows if many of those questions are coming in from the same location or from the same POP or worldwide, it's going to say no. Then nothing happens. And what happens is that an engineer gets a page. I'd much rather have a page because a malfunctioning robot like that and have to fix one bad hard drive here and there than having other pages because somehow my robot malfunctioned and decided to kill CloudFront. That's not something we want. Okay, that's what I had for today. Now I'm going to invite Shailu to the stage to continue the conversation.
Thank you, Georgie. Hello, everyone. I'm Shailendra Mishra. I'm a software development manager at CloudFront. What Georgie has been talking about, like these are the things that we do on a daily basis. We have to think about things that can fail and that can cause a drop in availability, right? So defense in depth is one of those strategies that we think about for every project that we work on. How do we ensure that what we're doing will not cause a drop in availability? Because as we mentioned earlier, after security, availability is like the most important thing for us. So before we talk more about that, Georgie very humbly, he pointed out he's the biggest threat to CloudFront. The reality is different, right? I'm a development manager. If there are any development managers here, you know this as well. We want our features to be done quickly, and then given to our customers so that we can get feedback. Development managers, we are always live in a world of happy paths. Edge cases don't happen, and it's quite natural. These edge cases, though, if you don't handle them, they can cause a massive problem. Right? So the whole point of defense in depth strategy is how do we ensure that even though something can skip by, how does our system prevent a drop in availability for us? So I'm going to present a case study, and we can go over some more details how it has helped us. And this is something that you can do in your systems as well. To provide a fancy title, right? To provide some more details about this case study, I need to explain what components go inside a CloudFront POP and how do they work with each other to make CloudFront what it is, right? It's a CDN, which means there has to be cache host. The cache host is where users will talk to when they want to download some content. And as Georgie mentioned earlier, DNS service, this is the service which will give out the IP address to the users. So let's say you have a user wants to make an HTTPS call to CloudFront to the cache host. Before they can do that, they need to go get an IP address, right? So far, so good. There is one critical component that is currently missing on the slides, and what we call traffic director. Traffic director, we have multiple instances of traffic director for redundancy purposes. But obviously at any given point of time, one of them is the owner, is the master. The traffic director is responsible for coming up with IP addresses, the list of IP addresses that actually goes to the DNS server, right? It's also responsible for giving out the same IP address list to the cache host. Now, the DNS service needs this because then that's what it will give out to the users. And why does the cache host need it? Well, the cache host needs this because during the TLS handshake, it has to give out the right certificate, right? So far, so good. The other thing that TD also does, it announces the IP list to the routers. And this is how any given CloudFront POP, comes into existence. That has TD in the POP, the traffic director, which announces its presence to the routers, and from there over BGP, everybody else finds out about it, right? So these things go together and make everything work. So what particularly happened in this case? Well, let's just say we had an unintended deployment of pre-production code, and it went to one POP. Let's call this POP A, right? And as we mentioned earlier, this is all waves and stripe-based deployment. So it's intentionally going to a wave which has a single POP, and if it fails, that's great. We can catch it and we can roll it back. That was the whole plan. Though the code that got deployed had some interesting side effects. I mentioned how we have a traffic director inside a POP, and it's a master-slave configuration. But after this code was deployed, the traffic director on one of the POP, it started announcing itself as the master, not just to the other traffic director hosts inside the POP, but also to traffic director hosts outside the POP, right? This is no good, right? As you can imagine, given all the things that traffic director does, this can be a really bad thing. And also, because it started announcing itself as master, now the traffic director hosts from other POPs, they started downloading the list of IP addresses from the master itself. So just think about that for a second. Given all the importance we talked about to TD and what happened here, I have some visual to explain a bit more. Before the code was deployed, let's say we have 3 POPs, they're all working fine. And then after the code is deployed, still the POP where the code was deployed is okay, but the unintended side effect of this is other POPs where no code got deployed, they started listening to the master on POP A. This is something we didn't even plan for, right? But this started happening. However, in spite of this, there was no impact to the data plane, right? And I'll explain about that a little bit more. This is where our the defense in depth that I've been talking about came into play. Our DNS servers, in addition to doing all the things that it does, it also validates the data that it gets from traffic director. And if something doesn't look right, something looks suspicious, it will just halt it. It will raise an alarm, right? This was done for other reasons. For example, as we are building new POPs, it's possible that we can do like a copy paste error. So the IP range is assigned to POP, you can just copy from somewhere else. But it really helped us in this case because truly what happened is the DNS server got the list of IPs meant for a different POP altogether. And that really helped us in this case. The other thing, the traffic director, even though it sends out IP list to the routers, it also validates what am I sending out. And if that doesn't look like, it stops the announcement. So really what happened was all the change propagation was halted. As a customer, if you made any changes to Cloudfront during this time, your changes were stuck. But any changes that had gone before that, they continued to work. And because we have this implicit assumption, right? Our engineers know about this, the entire management knows about this. We were willing to take control plane impact over data plane impact. So this is where knowing your principles is important as you design systems. Anyone who has used Cloudfront, they may have seen this in the past, and that's exactly what happened. It went into status of in progress and stayed in that way while all the existing requests were being served. So that's an example of what we call defense in depth. Even though you have software components that you trust, that's something that you have built, you still want to validate the data so that you don't cause an availability drop. The next thing I want to talk about is flash crowd. So flash crowds, they can be a threat to availability as well. In the past, they were called /dot effect, right? When /.org would link your blog or your website to their homepage, you would get this surge in traffic, and it was considered not a very common phenomenon. Though when you have a system like Cloudfront, which is deployed in so many cities across multiple countries, in 199 POPs, it's become very common. They happen on a regular basis. So let's talk about some examples. These were some events that were hosted on Cloudfront, right? Super Bowl in 2019, Game of Thrones, the final season. What happens right at the beginning of these shows is there's a huge surge in traffic, and it just behaves like flash crowd. So if you look at the graph, it goes from nominal to skyrocket traffic. It's something what we just termed itself as flash crowd. The other example is interactive TV game shows. It's very popular in Asia. We have anchors on TV who would ask a question, and then audience who's at home, they will use their mobile app, and they have like 10 seconds or something to answer the question. Now between those 10 seconds, if you look at the traffic, the surge in traffic towards the internet is crazy. Like it just behaves like as if there's a some sort of attack going on. No, it's just legitimate traffic. It's flash crowd. The third one, there used to be a time when synchronized clocks was very hard, but now with all the advancements in IoT, it's become very common. You can have IoT devices, and if they have been programmed in such a way that they all wake up at a certain time and they go download content from the internet, that also results in a surge in traffic, right? So if you own client stack for that, my request to you, please don't do it. It's just good for internet. Avoid it. Jitter is your friend. We'll talk about Jitter, in further slides, but please don't do it. All right. So those are good examples. But let's talk about how does Cloudfront handle flash crowd, and how you can handle flash crowd for your systems. Well, first of all, every POP that we run with enough spare capacity, right? This goes against Amazon frugality principle, but we try to have enough capacity so that we can handle flash crowds automatically. In fact, I would say more than 50% of all flash crowds just get unnoticed because we have enough capacity to just absorb them. However, if we know about the event, and if you've been working with customers, let's say Game of Thrones, we set up these configurations ahead of time so that the traffic, it doesn't get lasered onto a few POPs, but it's dispersed enough so there's a good mix of availability and performance for you, right? That is something we can do ahead of the event. However, let's say none of that happened and there is a surge in traffic. What happens at that point of time? Well, we have systems in place which will protect you from busy neighbors, right? You use Cloudfront for availability. That's like one of the key things that you want. And we want to make sure that some other distribution who's having a surge in traffic is not causing a drop on your availability. So we have systems in place that will kick in and they will throttle these requests. And then we have also built a service called Flash Crowd Mitigator. It's a very interesting service because it continuously looks at traffic for every distribution, and it tries to figure out if there is a huge change in traffic for this distribution over a period of time. And if it does detect that, then it will take its measures and it will try to disperse the traffic around. Like it keeps it around the same location so that there's no drop in performance, but it does its job every 10 minutes, continuously keeps working. And then lastly, within 20 minutes, and Georgie talked about this a little bit, our routing system, we measure the performance and the load from every link that we have data for, right? We use that information and then we generate a new system altogether and we push this data back to our DNS servers so that they can disperse the traffic. So, these are the things we do, things we do where we know about it, things where we don't know about it, we can immediately handle it. And then within 10 minutes, our flash crowd mitigator kicks in. And then finally, the routing system will definitely take care of any surge in traffic. Well, you can, do the same things. Like, as we talked about the synchronized internet devices, if you own the full stack, the client and the server, you can add some sort of a randomness, right? So that you don't query exactly at the same time. But if you don't control it, then my recommendation would be just use just use CloudFront. We will handle FlashCrowd for you. So talking about randomness, like jitter. Why is jitter important? This is something we pay a lot of attention to because it has helped us quite a bit. The idea here is to introduce a very small random thing into anything that you do. It could be like a periodic, timers, if you're doing retries, whatever that can result in a monoculture, figure out a way to break it. Like that is the whole point of adding a jitter. I'm going to explain this a bit more with a case study, right? So it becomes a bit more apparent. This is not something only CloudFront does, right? We use RAM disk to store configuration files. Configuration files, it's important that you fetch them and you load them into memory fast. So you don't want to use your SSDs for that. You can use your RAM for that. So we use RAM disk for this particular reason. Now, as your service is growing, as the number of customers is growing, as their configuration grows, these things grow in size. And because we have configured the RAM disk with an artificial limit, it's possible that the space will run out, right? It's a very common thing. And let's say if it happens across all the hosts at the same time, that can definitely result in a drop in availability. So what do we do in this case? Well, it might sound weird, but we have configured every single host with a slightly different RAM disk size, right? And this is a deliberate decision. We have done this so that anytime we run into this issue where the RAM disk fills up, we find out why this is happening. We sideline that one particular host, maybe worst case one POP, and then we take the mitigation efforts, right? But as an end users, then you don't see any drop in availability because we made a artificial decision saying, let's put this limit on the RAM disk. So just recap, like, where would you put jitters? As I said earlier, any place where you have artificial limits, think of adding a jitter. If you have timers, you have periodic async timers, you have retries, add some sort of a jitter to, basically to eliminate the monoculture. Now, word of caution, your jitter needs to be deterministic, right? You don't want something which is so hard to debug, that sort of random behavior, because that will be really, really interesting when your jitter actually causes more problems. The meta point being, try to avoid the monoculture. We do this in every system that we build. When we do design reviews, we talk about it, like, hey, how can we avoid so and so? And this is something you can also do. The next thing I want to talk about, and as I mentioned earlier, this presentation is all about, here are the various things that can impact availability and what does CloudFront do to eliminate them, right? Unfortunately, dependencies is one thing that you cannot eliminate in current modern software engineering. Everything that you build is probably on top of other systems that your team has built, that's built in open source, right? So you can't just eliminate everything. And especially if you use, anyone who has used NPM, they know, like, you try to install one module and it brings like another 15 modules with it. You are now implicitly taking dependency on those modules, right? This is a very interesting graph. It's 2 log axis, so it can be difficult to read. But one meta point is there are like 9,000 modules that have at least 5 additional modules that they pull in. So you got to be careful when you take those dependencies. At CloudFront, we definitely do that, right? We have our own internal package manager, and we have to be careful. If we don't pay attention to it, a simple hello world program might pull down a whole bunch of packages. So this is something that we pay attention to, our senior engineers pay attention to. In code reviews and design reviews, it gets called out, like, hey, don't take dependencies where it's not needed. So what if you said, okay, I'm going to build everything from scratch? Well, you can't really, right? Even if you just said, I'm going to write everything in assembly on hardware. Well, hardware is also kind of software, right? The recent Spectre meltdown, other things, they made it pretty obvious that you're taking a dependency on how those architecture is done, and hardware will fail on its own. So what about cloud services? Let's say you are building a new service and you want to take dependency on some cloud service. Well, keep in mind, cloud is nothing but hardware, software, and people, right? You are taking the dependency based on your use case. just be aware of it. Because as I said, you cannot eliminate dependencies in today's world. They are a necessary evil. Just be aware what you're getting into. And your availability will then be tied to the combined availability of all the dependencies that you rely on. So this next slide is essentially a recap. We talked about a lot of things that we do at Cloudfront and why we are proud of maintaining our high availability. These are the things that we do, but you can also do in your systems. Good CI/CD practices, like we shouldn't have to talk about it. It's super critical that we have these things in place. They will prevent more issues than you can imagine. Velocity checks. This is something we do at Cloudfront regularly, and that has helped prevent many issues before they actually go into production. Because by the time the deployment happens, it fails the velocity check and it never moves forward. And it makes us think, like, is this the right thing? Did we get the right config files, etc.? And even when velocity checks pass, and now the new configs have gone into production, right? The defense in depth really helps us, because even if the data is coming from our trusted systems, we still validate it. This one is an interesting point, because when you are building a system, you are thinking about how do I get this to production fast enough. And any check that you add for data coming from within your own systems, it feels like this is a waste of time. Why am I doing this? This is a trusted system. It's not supposed to send me that data. Well, it pays off. If availability is important to you, these things are worth it. It's worth doing it. Bad weather, like assume everything will fail. And Route 53 is one good way you can build like health checks. So if you have a system which is running, say, in US East 1 and US West 1, Route 53 can really help you do the availability checks and route your traffic accordingly, right? And then the next set of things that I want to call out, these come handy when you are building systems to take care of things that are failing, right? So our system, which automatically takes care of failing hard drives, what if that system has an issue and it tries to commit a mass suicide? You have to think about those things too and make sure that you don't accidentally allow everyone to die at the same time. And I think I've mentioned this before, Jitter, super important, see where you can add them. And finally, dependencies. You got to use them, so just be caution, use some caution on which dependencies you're using. So that's pretty much what Georgie and I had to cover in this presentation. There are more things that you can learn about. You can go to the link on the slide. You can go learn about Cloudfront. You can learn about networking. You can learn about how VPCs are configured. There's tons and tons of documentation. I highly recommend doing that. There is one other session, I believe it's today and also one tomorrow. It talks about how we provide high performance on Cloudfront. How today we talked about security and availability is like the number one things for us, but how do we do like highly performant distributed system? I highly recommend going there too. That's pretty much all I had. So thank you so much for coming. If you really liked the session, if you liked what we talked about, please take the survey. We'll appreciate your 5-star review on that. And we take your feedback super seriously. All right. Thank you so much.